Imagine a place in the universe where everything happens in reverse. A place that doesn't swallow but spits out. That doesn't trap light but rejects it. Sounds like science fiction? Well, that's exactly the kind of idea that theoretical physics, with all its complexity and boldness, has been flirting with for decades. The so-called white holes. If black holes are already terrifying by nature, their reverse siblings manage to be even more mysterious. But what exactly are these cosmic objects that no one has ever seen? Do they really exist? And even more intriguing, could they be connected to the beginning of everything, to the Big Bang itself? In this video, we're going to open a door to the depths of space-time and explore concepts so extreme that they put the known laws of physics to the test. Get ready to dive into ideas that challenge general relativity, quantum mechanics, and even our notion of time. Because at the end of the day, white holes might be much more than just a simple theoretical curiosity. They might be the key to one of the greatest mysteries of the cosmos. Black holes are, without exaggeration, the most terrifying creatures in the universe. Imagine a point in space where gravity is so intense that absolutely nothing, not even light, can escape. This is what we call the event horizon. Cross that invisible line, there's no way back. Anything that passes beyond that limit is doomed to head toward the singularity, where the laws of physics, as we know them, simply collapse. A true cosmic nightmare. And what's most unsettling? This monster doesn't have a surface, like a planet. You don't crash into a black hole head-on, you sink into it. It's like falling into a bottomless pit of space-time, where gravitational curvature becomes infinite. It was Albert Einstein himself, with his general relativity, who provided the mathematical foundation for these entities. But it was Karl Schwarzschild who, during World War I, found the solution that predicted these regions of absolute collapse. The most disturbing part? The information that goes in there never shows its face again. At least that's what we believed. Enter the famous information paradox, which shakes the very foundations of physics. Quantum mechanics says that information can never be destroyed, while relativity suggests the opposite. This clash between giants led to revolutionary ideas, like Hawking radiation, and even theories about black hole evaporation. And it's precisely this dilemma that leads us to an even more radical idea. If black holes are points of no return, white holes would be exactly the opposite. Regions where nothing can enter. No matter, no light, not even a stubborn particle escaping from the perfect vacuum. They would function as a kind of cosmic antithesis, expelling everything that approaches and maintaining their integrity in an almost arrogant way. While the black hole swallows, the white one spits. A concept that sounds absurd at first glance, but which is born from the same general relativity equations that gave rise to black holes. The idea is that these structures would absorb absolutely nothing. They would be like cosmic sources of matter and energy, firing particles non-stop, challenging our understanding of gravity and time. But don't be fooled. To this day, no white hole has been observed. We're talking about a purely theoretical construction, an elegant mathematical solution that emerges when physicists play with time in reverse. It's like watching a destruction movie in rewind, everything being undone in slow motion. What's curious is that this time reversal is more than just a conceptual trick. In theoretical terms, a white hole would be a black hole played backwards in time. This possibility opens the way for deep discussions about time reversal and about how the universe deals with the flow of time. And if you think all this is weird, just wait until we start exploring how this mathematical craziness can connect to secret tunnels through space-time. Yes, the famous wormholes. Now imagine this. What if a black hole wasn't the end of the line, but just an entrance door? What if, on the other side, what existed was a white hole, serving as an exit for everything that was swallowed? This is one of the most fascinating hypotheses in theoretical physics, the idea that these two extremes could form the ends of a wormhole, a cosmic shortcut between distant regions of the universe, or maybe between different universes. Sounds like science fiction? Maybe. But the mathematics allows for this kind of construction. This connection also plays a fundamental role in one of the hottest debates in modern physics, the information paradox. As we've seen, general relativity suggests that everything that crosses the event horizon is lost forever. Quantum mechanics, on the other hand, states loud and clear, information cannot be destroyed. How do we resolve this contradiction? Well, If what goes into a black hole eventually comes out through a white hole in another corner of the cosmos, information conservation can be restored. Nothing is lost. Everything, somehow, is transformed. If you're starting to realize how these ideas challenge everything we think we know about the universe, leave your like on this video. This helps us continue exploring these cosmic mysteries together. Science doesn't stop when it finds a limit. It provokes it. And when it comes to white holes, several alternative theories emerge to try to explain them or even predict them. A good example of this is loop quantum gravity, which suggests something surprising. After a process of black hole evaporation, these gravitational monsters could be reborn as white holes. It would be like a cosmic phoenix, where the end transforms into a new beginning. A bold proposal, but based on serious calculations. String theory, with its multidimensional approach and its fundamental vibrational elements, also enters the game. It suggests that space-time can behave in bizarre ways at extremely small scales. In this scenario, the singularities that today seem like absolute endpoints could be just passages, connections between universes or different states of our own. It's frontier physics, where the concept of a white hole as an exit from an interdimensional tunnel doesn't sound so absurd after all. And inside a black hole, the situation is even crazier. There, time and space switch roles. The singularity is no longer a place. It's a moment in the future, from which nothing escapes. In a white hole, this singularity would be something inaccessible in the past. It's such a radical inversion that it challenges our intuition. But if these ideas are correct, they might explain something even more fundamental about our own existence. Now comes one of the most intriguing comparisons in this whole story. What if the Big Bang, the starting point of our universe, has characteristics similar to those of a white hole? Think about it. Both involve a singularity. Both represent an explosive release of matter and energy. And, curiously, both mark a limit for time, just in opposite directions. The black hole is where time ends, the Big Bang, where it begins. This symmetry catches the attention of many theorists. This association doesn't mean that the Big Bang was a white hole, but there are those who argue that it looks like one, especially when we analyze its structure in light of general relativity. The universe would have been born from an extremely dense condition. In fractions of a second, everything expanded violently, as if it were being spit out of a cosmic funnel. This idea helps to mathematically model the origin of the universe, even though it leaves many questions unanswered. Of course, this is still highly speculative, but this kind of comparison is useful for testing the limits of our theories. If time can really have a beginning and an end, and if space-time can behave in such radical ways, then studying white holes might help us understand not just how the universe began, but why. And so, we continue challenging our certainties, pushing the boundaries of what we think we know about reality. But of course, not everything is roses in this whole story. As fascinating as the idea of white holes may be, the truth is that it faces a bunch of obstacles, and big ones. First, we've never seen one. No trace, no sign, no observational evidence. And look, we have telescopes pointed at the sky all the time, waiting for something unexpected to happen. The universe is noisy, full of extreme events, but so far no behavior that really matches a white hole. It's like looking for unicorns in forests that have already been completely mapped. Besides that, there's the environmental problem. To exist, a white hole would need to emerge in a perfect vacuum, free from any kind of surrounding matter. But the real universe is far from that. Even empty space is full of wandering particles, background radiation, and energy fields. The slightest external interference would be enough to make a white hole collapse and turn into, you know what happens? A black hole. In other words, even if they could emerge, they would be incredibly fragile. And there's still the dreaded second law of thermodynamics. According to it, entropy, the disorder of the system, always tends to increase. A white hole, by definition, would reduce local entropy, which is basically forbidden by the laws of classical physics. It's like watching a broken glass reassemble itself on the floor. That's why many physicists see white holes as beautiful mathematical fictions, but unlikely in the real world. But even being unlikely, they force us to think. And thinking is exactly what moves science forward. Even without concrete proof, white holes continue to haunt and inspire physicists around the world. They're like distorted mirrors of black holes, forcing science to look at its own limits. And maybe that's exactly what's most valuable, forcing us to rethink what we understand about time, information, and even the universe itself. Deep down, they're like questions disguised as answers, enigmas that challenge logic and inflate curiosity. Whether through general relativity, string theory, or the bold loop quantum gravity, what matters is that white holes keep alive an essential flame of science: doubt. By imagining these phenomena that would spit out matter instead of swallowing it, we test our models, provoke new ideas, and maybe get a little closer to the truths hidden in the fabric of space-time. After all, understanding what doesn't exist can be as revealing as studying what does exist. And now, the question remains: will we one day find evidence of these white ghosts in the sky? Or will they continue as pieces of a puzzle that we still don't know how to put together? What's certain is that each new hypothesis pushes us one step forward toward a more unified, bolder, and more connected physics with the origins of the cosmos. If this journey through the mysteries of the universe sparked your curiosity as much as ours, don't forget to subscribe to the channel and hit the notification bell. We have much more to explore together in the depths of the cosmos. Leave us in the comments. Which theory about white holes impressed you the most? See you in the next video. Because knowledge is just the beginning.